All right, folks, so let's pick up with A to D and D to A conversion. So remember that we are going from the real world in terms of analog into the digital world in terms of binary numbers. And so if I have some sinusoidal voltage being applied by some sort of sensor and I want to convert it into a binary number at each point, well, how often am I going to sample? Let's assume that we're sampling every 1 second. So I'm going to grab the values every 1 second. And you can see as I'm filling these in that I'm not picking up anything between those samples. Of course, if I'm only sampling at 1 second, what happens at 0.5 seconds? I don't know. Also, those values are losing everything in terms of voltage between them. So we are losing information when we do this sampling, and that's something that we had pointed out before. Hopefully we're sampling fast enough that the information loss is relatively small. So as we're converting this to these binary numbers, we know that they're going to be binary, but for the purpose of making things easy to write out, we are going to use a decimal equivalent. So on the following slides, assume that it's a decimal equivalent. So I've got a number line, the same sort of thing as previously. So I've got this number line where I have an incoming voltage from the real world, and I'm converting it into a code in the microcontroller, the digital world. And so that incoming voltage could be anywhere in there between the minimum and the maximum voltage levels, and the digital code will be somewhere in terms of unipolar from 0 up to 2 to the n minus 1, or in terms of bipolar from our negative 2 to the n minus 1 up to 2 to the n minus 1 minus 1. So for instance, I might, in this particular case, have negative 4, negative 3, negative 2, negative 1, 0. There's my 0 point. 1, 2, and 3. And so you can see in this particular example that input voltage would get mapped to a negative 1 code, which, depending on whatever scheme I've got, however many bits I've got, you can map that to a digital, to a binary number. So what I want to do is I want to be able to talk about the smallest numbers that I can represent, the smallest divisions between these digital representations. So the smallest voltage division is going to be called the quantization interval. So you can see that's the width of a voltage range that gets mapped to the same digital code. So again, this was negative 4, negative 3, negative 2, negative 1. So the width of my negative 2 bucket is the quantization interval Q, and it is measured in terms of voltage. Also, I've got the offset voltage, and the offset voltage is whatever voltage is going to correspond to a code of 0. So in terms of my bipolar representation here, you can see that that one is going to be the voltage that corresponds to 0 code, so we're going to call that the offset voltage. When we deal with the unipolar case, it would be down here. So it is different between the unipolar and the bipolar cases. If I want to calculate the quantization interval, probably shouldn't have sketched over my equation there. If I want to calculate this, you can see that what I'm doing is taking my total voltage range and dividing it by the number of buckets. So the maximum voltage minus the minimum voltage divided by 2 to the n minus 1, the number of buckets that I've got. So that gives me Q, the quantization interval, and V offset. So we'll use those, and so let's start with unipolar codes, and then we'll go to bipolar codes, obviously. So let's start with unipolar codes, and so if I want to map an input voltage into a code, well, this is a mapping problem. We're mapping a point on one side of the number line to a point on the other side of the number line. So if we think about this in terms of the distance between the input voltage and the offset compared to the entire range, well, that's going to be the difference between Vn and V offset divided by VADC max minus VADC min. So we can divide that by the difference between 0 and our appropriate code, and 2 to the n minus 1 minus 0, which is our total range. And we do have to round it, of course, because we're going to binary numbers that are going to be whole numbers here. So we can simplify this because we know this thing is Q. So we can say that the code is going to be rounding Vn minus VADC min over Q. So what if we want to do a bipolar code? Well, same sort of idea. We're going to take it relative to the offset again, which in this case is going to be 0 voltage. We're going to assume that the offset is always going to be 0 voltage for our bipolar codes. And so the bipolar code will be the rounding of Vn minus 0 divided by Q. So there we go. We got, flip back here, Vn minus VADC min over Q, and Vn minus 0 over Q, and both times we round. So here's a real simple example. If we've got a 3-bit ADC, it's not a good ADC, it's an easy one for an example. We've got a minimum voltage of -2, a maximum voltage of 1.5, and then an input voltage of 1.25. Figure out what the appropriate code is going to be if you use only unipolar or you use bipolar codes. So you can work through the math, pause the video, work through the math. And what you should get is that Q is half a volt. And so in my unipolar case, I'm going to put in the numbers here. So 1.25 minus the -2 volts divided by half a volt is going to be either 6 or 7. Well, which one is it going to be? This is a good question. So if you are looking at this and you say, well, it's 6.5, which way do I round? A lot of people are going to say, I'm going to round up. Well, why would you round up? That's what you learn in grade school a lot. But this is a problem in terms of bias in your rounding. So go back and look at the IEEE standard for rounding, and there's something called banker's rounding. So banker's rounding says that when you get you're rounding on a 5. So if you're rounding on 6.5, you're looking at that 5. So if you always rounded the 5 up, then you will consistently bias your results up. And so the IEEE standard says that when you have exactly a 5 that you're rounding on, instead of always rounding it up, you should round it to the nearest even number. And so in this case, it would be 6, not 7. So we can do the same thing in terms of our bipolar. So again, you can work through the math. And so we go 2 or 3. Let's use our convention, our IEEE standard for rounding, so we get 2. All right. Whoops, stuff was out of order. Sorry. So if we've got a code and we want to go back to a voltage, notice that when we go back to a voltage, it's going to always be the voltage at the center of the range. So it's an estimated voltage. And so we'll just do our math in reverse. And so our estimated voltage is going to be our code times Q plus our offset. But what that doesn't tell us is where it actually was. So it was somewhere in that range, but we know the center point, and so we know that there's an error associated with that. And so we know that we've got our quantization interval, and so we talk about the quantization error as being half that interval, because we know that any input voltage in that range between V and hat, the estimated input voltage, plus or minus Q by 2, was going to have the same estimated voltage. So anything in that range would get mapped to the same code. So if we have that code, then we know that our input voltage was somewhere in that range of V and hat plus or minus Q over 2. So Q over 2 is what we call the quantization error. So if I've got a 3-bit ADC, I've got a minimum voltage of 0 and a maximum of 3.5 and a code of 2, what was the estimated input value, input voltage? So again, Q is going to end up being a half a volt. And then if we work out our estimated voltage, you should get 1 plus or minus a quarter volt. So we don't know exactly where it was, but it was somewhere in that range. So notice that in each of these examples, you can see that the maximum voltage ends up being something that's down a half a volt from an even number. So 0 to 3.5. Not 0 to 4, but 0 to 3.5. Why is that? Well, that's the difference between what we call nominal and true range. So a lot of times with things like the Arduino, you're going to see them quoting the input range in terms of nice round numbers, 0 to 5 volts, -10 to +10 volts. Well, that is what we call the nominal range. The true range is not exactly that. So the true range is based on the fact that you only have up to 2 to the n minus 1 bins. So let's look at the Arduino and the unipolar case. So we go 0, 1, 2, 3, 4, 5, 6, 7. I know there's more than 7 numbers on the Arduino, but in this case with this simple 3-bit example. So we get all the way up here, and then we're missing number 8, of course, because we've only got 8 total, and so if we included number 8, that'd be 9, and that wouldn't fit within our 3 bits. But if we think about the example we were just doing, we have 0 volts, 0.5 volts, 1 volt, 2 volt, 3 volt, and then this last one is 3.5 volts, and 4 volts is out here associated with a code that doesn't exist. And so the same sort of thing occurs when you think about the Arduino going 0 to 5 volts and being in 10 bits, you end up with that 5 volts at the end being associated with a code that doesn't exist. And so what it really should have been is listed as 0 volts up to 5 minus Q volts, but nobody wants to write out that kind of precision, so they often will write it out as just this up to 5 volts. And everybody understands that they're talking about the nominal range instead of the true range. So when we're thinking about these ranges, we have to make sure we know which one we're dealing with. So the equation I gave you before for the Q value was based on the true range. So that was taking that true span and divided by 2 to the n minus 1. If instead you're using the nominal, those nice round numbers, remember that they're assuming an additional code that doesn't exist. So instead of going 2 to the n minus 1, you need to go up to 2 to the n. So if you have the nominal, divide by 2 to the n. If you have the true, with the one that's messy and not evenly written out, is 2 to the n minus 1. So almost everything is going to be quoted in terms of nominal range. Just understand that and make sure that you're using the right one. So we'll stop it here and we'll go on to the next video.